From previous videos, we already know that the amount of current is not the same everywhere in a parallel circuit. There's more in some places and less in others. I want to look at where there will be more and why in this circuit, and probably in this video, and including a thing called short circuits. I want to look at those. Now, first, how do we define a resistance in the previous video? We defined it as opposition to current. You could say resistance to current. Opposition is probably a better word. We had this silly picture here. Mr. Current walking along here happily, and all of a sudden Mr. Resistance starts to oppose him. Resistance opposes current. Now look at this diagram here. Which leg will have more current? You could ask that a different way. Which leg has less resistance to current? It's pretty clear, isn't it? Leg 2 has less resistance to current, only 4 ohms. Leg 1 has 6 ohms. So wouldn't common sense tell you we would expect to have more current here in leg 2? Because there's less resistance or opposition to current. Yeah. Let's read this. Leg 2 has less resistance to current. Less resistance period, right? 4 rather than 6. So leg 2 should have more current, correct? I believe so. You ever heard of the term the path of least resistance? It's often used to describe people who don't like hard work. They'll just do the easiest possible thing, even if it's not the best. Here's where it comes from. It comes from circuits. You could call this the path of least resistance. It'll get more current. So let's do a couple calculations to find out how much. Recall in a parallel circuit that the voltage up here at the top of each leg is the same as the battery, 12. It's got to be 0 when it comes back here, so these are 0. So our voltage here in both legs is 12 minus 0. Voltage, 12 minus 0 is 12 volts. In this one, leg 1, the resistance is 6 ohms, and we're looking for current. Easy enough to use that formula. Plug in. We get 2 amps in leg 1. The same kind of calculation. We have less resistance here, so that number in the bottom here is smaller, and we'll get 3 amps. So here is the reading in all these ammeters. We already said that 2 is here on leg 1, 3 is here on leg 2, and the outside ones are easy because that 2 and that 3 comes together in a join, doesn't it? You add it to 5. If this is going to, where we have here, if that's going to split into 2 and 3, it must be 5 also, right? So the outside ones are pretty easy to find once you calculate the currents of the legs. Now what about here? What would happen here? There's no resistor here, is there? Again, ask yourself about the resistance to current in each leg. Where is there less resistance? Well, obviously that guy there. In fact, there's no resistance, right? I've covered up this part of the circuit because it doesn't exist. All the current will come down through here. There's no resistance. It will all come here. Now let's try doing a little current calculation here on this leg here. The voltage is 12, right? What's the resistance? 0. There's none. Division by 0 creates infinity, doesn't it? Well, in circuits it causes trouble. And that trouble has a name. It's called a short circuit. All that current will come down here and it could melt the wire, destroy the circuit. Now there are 2 ways to address a short circuit. The first way is use what's called a fuse. Today we use circuit breakers more, but a fuse is kind of flimsy, probably a piece of metal. And if we had this sudden short circuit and a lot of current come down through here, a whole lot, this would burn out and save the circuit. Today we use circuit breakers more than fuses, and they would pop open and save the circuit. So you could do that by designing your circuit. And there's another way. How about this? Put a resistor in the freaking leg. Yeah, I put one here, haven't I? So now this will get more current here because it has less resistance, but it's not going to be some gigantic number. In fact, I think it would be probably 12 over 2. It would be 6 amps, which is a lot, but probably won't destroy the thing. So put a resistor in here. That's the best way, probably. All right, so here's a summary. In a parallel circuit where there's less resistance, there's more current. Less resistance, 3 amps. 6 amps, 6 ohms, more resistance, less current. And the other thing is that if you have no resistance, that's going to be called a short circuit. Could damage your circuit unless you have the fuse. And the best way to do that, to avoid this, of course, is to put a resistor in there. Bye.